Hi everyone, welcome back to another video. In today's video, I'm going to be talking about imperfections in solids. Well, we'll start with this video on a very beautiful note by a quote by Mr. Stephen Hawking, which basically states that nothing ever is perfect. In this video, we'll talk about solids and how they're not perfect, but in life, in reality, it's just better if we just accept it now. Okay, so enough of the philosophy here. We'll start with the video. So what we know as of now is that in case of crystalline solids, everything should be very perfect. The arrangement of constituent particles, which can be atoms, molecules, and ions, they should be perfect, right? Something like this is what we imagine, right? But in reality, it's not like that. Okay, perfection is okay. I mean, solids should be perfectly arranged, ordered structure, long range order should be there. But this does not happen unless and until it is 0 Kelvin. Only at 0 Kelvin will you observe that, okay, fine, the particles are at whatever space they should definitely be at, right? But in the real case scenario, in the scenario which we see around all of us, we have something called defects, okay? What is a defect? Defect is something which is just a deviation from the ordered arrangement. That's called a defect, okay? And these defects or these imperfections are going to actually give new properties to a solid. We'll see all that how, but you just need to know that, right? Okay, so these defects are of 3 types if we just classify them. Stoichiometric defects, impurity defects, and non-stoichiometric defects, okay? And it's important to know that all of them are included into the point defects category. So what is a point defect? Whenever in a crystalline lattice, there is a defect at points, okay, which is at lattice points, that defects are called as point defects. Whereas when we have defects in the entire line of, atoms or molecules or ions, that is called a line defect, which is not going to be part of this video today, which means we are going to be only discussing the point defects here. Okay, so if we talk about the stoichiometric defects, okay, well, these will not destroy the stoichiometry of the solid. Now, what is stoichiometry? So if we just, if I just write over here, NaCl, okay, which is salt. So if I write NaCl, which means for every 1 sodium ion, there should be 1 chloride ion. This is the stoichiometry of this NaCl solid, okay? And but if there's any less sodium ions present or any higher amount of sodium ions present for 1 chloride ion, that is going to be a wrong stoichiometry, okay? So these defects will not play with the stoichiometry, and they are also called thermodynamic defects or intrinsic defects. All right. Now, these are of 2 types, that is vacancy defects and interstitial defects. Well, I think it's very clear with the name that vacancy defect is something which is going to be like maybe at some point, at some place in a solid, in a lattice point, there should be some atom, molecular ion, and it is not there. It is a vacant place, and that is what a vacancy defect should be. And interstitial means that instead of being at a lattice point or lattice site, it is there somewhere in between. So we'll discuss all that in detail. I'm just saying all this, in a flow, but we'll discuss all this in detail, okay? All right. But electroneutrality should always be maintained. So no matter what defect we're talking about, stoichiometry, impurity, or non-stoichiometry, we do not get an electric shock when we touch salt. Do we? I don't think so, okay? So which means because of course if salt is electrically neutral, it is not having any excess charges, means it is electrically neutral and it is not going to give us a shock if we touch it, right? So which means everything which we see around us is electrically neutral, we just don't get a shock touching anything, right? So which means every defect is going to be will be accepting the fact that electroneutrality should be maintained, and no defect is going to contradict that. Alright, so let's discuss what are these Frenkel defects, okay? This is what a perfect crystal looks like. Perfect or close to perfect, because we know how perfection is something which is not achievable. So this is what a close to perfect crystal looks like. Now, it's possible for these cations, the orange ones. So I'm calling these orange ones as cations because they're smaller in size, and the bigger ones as anions because, well, they're bigger in size. And you should know why, okay? If you do not know it, then you can comment that down below. I'll try to answer that, but that's the case now. Now, it's possible for these positive charges to move or to dislocate from the point that they are present in to a new point in the crystal or the interstices of the crystal, something like this, okay? So this place where the cation was initially present, it has moved from this place to a new place here, and now from the point it has moved this place, okay? There's a vacancy that is created, so here we have a vacancy defect, okay? And to the place which it has now moved, okay, now we have an excess cation there, okay? So that is an interstitial defect. So what we have already discussed, we have two types of defects, vacancy and interstitial defects. Frenkel defects is actually a combination of both. We have vacancy at the point where it should have been present and interstitial defect at the point where it is now present, right? Okay. So in case of Frenkel defects, it is also called dislocation defect because very clearly it's just nothing but a dislocation of the cation from one point to another, right? Second thing is does not change the density. Why will it change the density, right? Because density depends upon mass and volume, and because there is no change in mass, because whatever the mass was initially there, it's still that mass only, because it's just a dislocation, okay, not a complete vacancy. It's a dislocation from one point to another, so mass is exactly the same. So density of course is not going to be affected, okay. And then it can only exist when there's a large difference between the cation and anion. Of course, okay, if the cation is really small, only then it can, be moving from one place to another. If it's big enough, how will it move, right? So if it's big enough, just like an ion, then it is not going to be free to move and the Frenkel defects would not take place. But since it is small, only then it is able to move. So it is only possible, Frenkel defects are only possible when there is a large difference in the size of cations and anions. Now we have examples like ZNS, AgCl, AgBr, AgI. Okay, so you'll notice that I have highlighted AgBr in a while. You'll know why. Okay, so all these different solids have a higher difference in the sizes of cations and anions. That's why we have Frenkel defects there. Now let's understand what is Schottky defects. Before that, we should know that electron neutrality is always maintained, because whatever it's just shifting, it's just dislocation. There's no alteration in the charge. Okay. Now we have Schottky defects. What is a Schottky defects? This is a perfect crystal. Again, in case of Schottky defects, we have a close to perfect crystal. Okay. Now, what if there is a vacancy of a cation? Okay. And vacancy is complete vacancy. The cation is actually out of the crystal now. It's not even there somewhere in the interstitial area. It's completely out. Okay. If that happens, then the solid will have an excess negative charge, because if one cation is gone, there will be one extra negative charge, and as and when we touch the solid, we'll be getting electric shock. But that does not happen, right? So that is why whenever there is going to be a cation less, the same number of anions have to move out of the crystal so as to maintain electrical neutrality, right? Which is a rule which we have to always follow. So what will happen is, whenever a perfect crystal is there and there is one anion which decides to, or cation which decides to move out, there will be the same number of anions which will definitely have to move out, and that is what a Schottky crystal looks like. Okay, this is nothing but just a vacancy defect in ionic solids. It's complete vacancy. There's no interstitial defect here. It's only vacancy defect here, unlike in case of Frenkel defects. It decreases the density, of course, because now we have a decrease in the mass, because we have one cation and one anion less. In this case, we have only one less, but in actual case scenarios, we have like a number of cations and anions which are completely gone out, right? So now it exists in examples like NaCl, KCl, CaCl, and again AgBr. So now AgBr is one example, which is an example of both Schottky as well as Frenkel. This is something which can be asked in competitive exams. That's why it is highlighted. Thank you so much. All right. Again, electron neutrality is always maintained, and because of that, we have, how one cation is gone and one anion, of course, has to go. So that's what is also accepted here. All right. Next, we have impurity defects. The second type of defects is called the impurity defects. Now, this is what an NaCl crystal looks like. Okay, so we have Na and Cl. The stoichiometry is something like this: NaCl. Na is having +1 charge and Cl is having -1 charge. Okay. Now, strontium is another element which is having a charge of +2. If I decide to replace some sodium positive ions with strontium ions, okay, since strontium is having a charge of +2, unlike your sodium which is having a charge of +1, if it is trying to replace sodium positive, then of course 2 sodium will have to go out, okay, so as for 1 strontium to come in. Is that clear? Because of course electrical neutrality, our rule has to be maintained. Okay, so because here 2 will have a charge of +2, only 1 has a charge of +2, so to electrical neutrality, to maintain that, we need to have that 2 sodium have to go out in place of 1 strontium which is going to come in. Okay, so if I replace 1 sodium with strontium, 1 extra sodium has to go out, and that place is going to be vacant, right? This is vacancy which is created because so as to maintain electrical neutrality. So this is called impurity defect, in which we are adding another element as an impurity into our existing solid, and it is a vacancy defect at the cationic sites. Each strontium plus is replaced by 2 sodium plus 1, because of course to maintain electrical neutrality. And examples are CdCl2 and AgCl. The same thing is going to happen if you just add AgCl crystals into CdCl2 crystals, right? Okay. Now we have non-stoichiometric defects. Again, non-stoichiometric defects are going to play with the stoichiometry. They are not going to be in accordance with stoichiometry. They will definitely be changing the stoichiometry of the crystal. Let's see how. So this is NaCl, okay? NaCl mein, as I already discussed, Na is 1 and Cl is also 1. So for every 1 Na, there should be 1 Cl, and if it's any less or any higher than that, of course the stoichiometry is not right, okay? Na here is the metal and Cl, chloride here is the non-metal, okay? Now, these defects can be of 2 types. Metal excess, either the metal can be excess, okay? In this case, it is 1:1, but maybe it is higher than 1, so it is going to be metal excess. Or it is metal deficient. In this case, maybe it is going to be less than 1 and Cl is going to be 1. So that's metal deficient defect. Okay, let's talk about the metal excess defects. In metal excess defects, also it can be of 2 types. It is anionic vacancies. If there's anions are going to be less, of course metal is going to be high, right? So that is going to be one case. And second is extra cations. Of course, if cations is going to be high, it means metal is high. Okay, so again the main rule is followed. Electroneutrality always has to be maintained no matter what. Now this is what a sodium chloride crystal looks like, okay? Now if we are going to heat it in presence of sodium vapor, what happens is, so this is sodium vapor, right? Now sodium vapor is having sodium atoms. Now sodium atom is never stable. It is always going to convert into sodium plus and 1 electron, because it has to do that. It is something which is tendency, okay? Now what happens is, when sodium is present, it is going to convert into sodium plus ion, and 1 Cl chloride, okay, from the lattice is going to move from here to this sodium so as to form sodium chloride there, okay? Now this sodium, to form sodium chloride, this is already Cl minus, okay? To form sodium chloride, this sodium has to become Na plus, okay? So it is going to give out 1 electron, and that 1 electron is going to go and sit there at the site of vacancy of the chloride, okay? And this site is called as F center or Farben-Center center. This is something which is asked mostly in the competitive exam, so you can highlight that. And because of this F centers, it imparts some color to the sodium chloride when it is heated. It becomes yellow in color, okay? So the reason of the yellow color is because of the F center, and when we heat it, what happens is these electrons are excited, and when they come back to original state, they give out some light, and that is what you see as the yellow color, okay? The same thing happens when lithium chloride is heated, okay? Pink color you can see, and when KCl is heated, you see violet color. That's why you see a beautiful, image on the first slide of this video. Actually, it's a GIF where you see different solids being heated, right? Okay. Again, these are anionic vacancies, okay? Okay, so now let's have a look at what happens when there are extra cations. So we have done when there is less number of anions, okay? As an example of NaCl and F centers, we have done that. Now let's see what happens when there are extra cations, okay? So the most important example is zinc oxide heating. So when zinc oxide, which is white in color, okay, when it is heated, it becomes yellow, okay? The reason for it becoming yellow is this, that when it is heated, it loses oxygen. So this oxygen is lost and it is gone in air, and what we have is, we have extra amount of zinc 2+ cations and the electrons, and both of them go into the interstitial sites, okay? And when they are heated, these electrons are excited, and when they come down to the lower energy state, they give a color, okay? So I don't think it's a rocket science here. The most important example here is zinc oxide and its heating, and that is an example of extra cations defect. Now we have the last one, which is metal deficiency effect. So we have done what is metal excess defect of 2 types, anionic deficiency and extra cations. Now we have metal deficiency defect. Now metal deficiency defect is kind of an inherent defect, because it is something which is made, it is something which comes at the time of making of the crystal. So when we make ferrous oxide, FeO, okay, we know ferrous iron is present in 2 oxygen state, which is +2 and +3, right? So when we are trying to make ferrous oxide, which means Fe2+ and oxygen O2-, okay, at that time, from the making of the crystal, it is very difficult to keep the stoichiometry 1:1. Okay, according to the formula, it should be 1:1, okay, but it is mostly not that, and mostly iron is always less. Fe2 plus is always less, okay. This is something which is inherent, okay, and this gives rise to the metal deficiency defect, okay. So this is the most important example here of FeO crystal, and this was all about impurity in stoichiometry, impurity in solids, and well, if you have any doubts, you can comment that down below. I'll try to answer them. If you want to watch more videos like this, follow this page, and thank you so much for watching. Stay tuned for more.